Okay, let's continue the discussion on least square approximation, and we have defined the error between the given v vector and the linear combination of this v sub k vectors, and we would like to find the optimal coefficient alpha k that minimize this error. And we know that to do that we need we need to set the partial derivatives of this energy with respect to alpha j equal to 0 for all the alpha j coefficient from j1 to n. And not only that, but then we also have to make sure that this stationary point that we found, if they exist, and we found them, we need to make sure that they're also giving a local minimum, and let's see also if they are conditioned for the absolute minimum. But before doing that, let's manipulate this expression and read it let's write it in a different form. So this error is basically a function of the n parameters, and we can rewrite it as v minus the sum from k equal 1 to n of alpha k v sub k, comma, v minus sum from k equal 1 to n of alpha k vk. Now I can take advantage of the bilinearity of the dot product and write this length as v dotted with this, v dotted with, interchanging the notation between v1 comma v2 equal v1 dot v2. These are identical for us, okay? They're the same things. It just it's gonna help me to condensate the expression, and I don't have to write longer expressions, okay? So we have to do v dotted v, and then I have to do v dotted with minus this vector, so minus v dotted with k 1 to n of alpha k vk, and then I have to do this dotted with that, but at the end of the day this is exactly the same as this because the dot product is symmetric in the two arguments, so it's just simply minus 2v dotted with this, and then I have minus minus plus the sum from k equal 1 to n of alpha k vk multiplied by, let's use another index, let's call it h from 1 to n of alpha h v sub h. Okay, now we can do further, we can do a further simplification, because this is nothing else than the length of the vector v square, and here I can swap the dot product with the sum because they are linear as operators, and so write this as 2 times the sum from k equal 1 to n of alpha k v dotted with vk plus the double sum from k equal 1 to n and also h equal 1 to n of alpha k alpha h vk dotted vh. Nice. So now we start to see the structure of this function with respect to this coefficient alpha 1 alpha n. So this error is given by the original length, the length of the given vector v that we have and we know, this is just a number, minus 2 times k equal 1 to n of v dot vk alpha k plus the double sum from kh equal 1 to n of vh dot vk alpha h alpha k. Now you can see that this is the function of an hyperboloid, okay, in I dimensions, of a paraboloid in of a high dimensional paraboloid, high dimensional paraboloid in I dimension, okay, because we have n parameters, okay, high dimensional paraboloid in terms of the alpha k coefficient. Indeed, if we restrict, for example, if we just have two coefficients for n equal 2, we simply have epsilon alpha 1 alpha 2 is equal to the norm of v square minus 2 v dotted v1 alpha 1 minus 2 v dotted v2 alpha 2 plus now we have all the v1 dot v1 alpha 1 square plus v2 dot v2 alpha 2 square plus twice v1 dotted v2 alpha 1 alpha 2. If you look carefully at the structure of this function, you will see that all these coefficients are positive because they represent the length of the respective vector v1, v2, and v1 and v2. And so this is actually in 3D, if we plot it, alpha 1 and alpha 2, and this is the error, this is exactly as some is a paraboloid, is the classical 3D paraboloid. Indeed, you see that if I fix the energy epsilon and I cut with epsilon equal constant plane, the section is going to be a circle, which is very clearly from here. Now you can see the structure of the classical equation for the definition of a circle. Okay, and then you see that for sure we know where it's going to be the minimum, because it's going to be the pole of the paraboloid, and actually it's going to be only one local minimum. And so when we compute the derivative, the epsilon with respect to alpha 1, you see that we're going to get immediately what? We're going to get 2 v1 squared alpha 1 minus 2 v dotted v1 and then the epsilon, the alpha 2 equal to I forgot that we also have an extra term here, that let me do it correctly. Actually, no, there is, we're going to do it in general, okay? So there is no need to, we're going to derive these derivatives for the general case for given generic n, okay? So here I just want to show you that the structure of this function as a function of alpha 1 and alpha 2 represent in a three-dimensional domain, represent a paraboloid. So we get to the idea that there will be a unique local minimum, okay, which is also the absolute minimum. And that's why it is called least square, okay. Now let's go back to this to the original function, which is given in this form, and we want to minimize this function. So the energy alpha 1 alpha n equal minus 2, so k1 n, so I'm going to write this v dotted dk alpha k plus the double sum k equal h to n of vh dot dk alpha h alpha k. And let's do the derivatives. The epsilon alpha j equal, so So now I fix one coefficient, the alpha j coefficient, and I take the derivative with respect to this coefficient. This term doesn't depend upon the derivative, so it doesn't depend upon alpha j, will not give any contribution. Here we have a sum of n terms, and the derivative with respect to alpha j will be simply minus 2 v dotted vj. I only pick the j term. Here I have a double sum, so I have to be careful. I first fix h, so I have plus the sum from h equal 1 to n, and I have h terms, but then among the k terms I only pick the j term, so I'm going to have vh dotted with vj times alpha h. Okay, because the derivative with respect to vj, is in the it's going to be with respect to k, so I will end up with alpha sub h. And then I do the same. Then I do the other index from k equal 1 to n. Now I can run vk dotted among the h terms. I only pick the term when h is equal to j. So we'll have v sub j alpha k. And of course we want this quantity to be 0. Now you see that this term and these terms are basically the same. It's just, I'm using a different index. So I can rewrite this quantity as minus 2 v dot vj plus the sum from k equal 1 to n of vk dot vj times alpha k has to be equal to 0 from j equal 1 to n. So what we got here is basically a linear system to solve for the n alpha k coefficient. And sorry, here is double 2, I forgot. So 2 and 2 simplify. So we have v dot vj from j equal 1 to n. So that's a very nice result, because now this is linear algebra. So let's see what is the structure of this system. Let's rewrite it in a generic form, in a matrix form. So here we have v1 dot v1, v1 dot v2, v1 dot vn, v sub n. Then here I have v2 dot v1, v2 dot v2, v2 dot vn, and so on. So you see we get this this matrix, which in general is going to be a full matrix. Of what? In the coefficient alpha 1, alpha 2, alpha n, and then the right hand side is given by v dot v1, v dot v2, v dot vn. Nice. So of course we know that for the system to admit a solution, the determinant of this matrix, that I'm going to call it G, which is basically the Gramian matrix from Gram that studied this problem. The determinant of G should be not 0. Okay? Determinant of G should not be 0. Okay? So we need to have the determinant of the matrix G should be different than 0 in order to have solutions. Okay? And this implies simply that the vectors v1 and v sub n are linearly independent. Okay? And vice versa. So this is also, you can even prove it. And you can clearly see this because you see that each of these coefficients, more or except for the diagonal terms, the extra diagonal terms, they're simply telling me they are proportional to the projection of V2 onto V1, of Vn onto V1, and so on. So you can picture each of the columns as the projection of V1 onto the others vectors. And if the determinant is 0, it means that any of these two columns will be linearly independent. Okay? And this implies that some projection between the two vectors, they are proportional, and then you lose basically the linear independence. So that's very easy to show. Of course, that will be the general matrix that you would get, for example, when you have when you try to solve finite elements, for example. Finite elements, is based on least square approximation, and you usually get not necessarily full matrices, but they are bounded. Okay. Ideally, we would like to have an easy solution of this problem. Is right? The easy solution would be when G is a diagonal matrix. How can we make G diagonal? We can make G diagonal by imposing that Vn dotted with Vm is equal to 0 when n is different than m. So the G is diagonal when the vector V sub k are orthogonal. Because now you see that all these terms simplify, and we are left with the diagonal terms, and then the solution is pretty straightforward, because alpha k is equal to V dotted Vk divided the norm of Vk square. Okay, and this is what we call the projection of V onto Vk. That's how we define it before. And this basically conclude this review on least square approximation. Okay, thank you.